Yes, hello students. In my previous two lectures, I explained the rectifier controlled DC motor drive, and we had seen that there are two possible modes of conduction, that is continuous conduction mode and discontinuous conduction mode. And we had drawn the waveforms of armature voltage and current for both the cases and discussed this in detail. So today we shall discuss what is the characteristics of a DC motor fed from a rectifier. So, you recall the speed versus torque relation that we derived earlier, and this was average value of armature voltage divided by a constant K, that is Ke into phi, minus Ra upon K square into tau. That was the basic equation for speed versus torque characteristics. Now here, for continuous conduction, we have shown that for single phase rectifier, Va is equal to 2 Vm by pi cos alpha, where alpha is the firing angle of the thyristors and Vm is the peak value of the source voltage. So if you put this value here in this equation, you get the relation omega m equal to 2 Vm by pi k into cos phi minus Ra upon k square torque. So this relation is for continuous conduction, and you can see that for a particular value of alpha, this is a constant, average value of the voltage will remain constant, and that is nothing but the no load speed. So this y-intercept of this linear relationship is constant irrespective of value of alpha. If alpha remains constant, it will remain constant. So as the load varies, the speed will drop because of the negative slope here, minus Ra upon k square. So the speed torque characteristic is normal, as it was for the normal DC motor fed from a DC supply. So this is like that. For one value of alpha, you are getting this characteristics, and if alpha is varied, the slope doesn't vary, slope remains the same. Only the y-intercept of this characteristic will change, and the characteristic will shift downward as it did for the normal operation. So this is the characteristic for various values of alpha, 0, 60 degrees, and then this is for alpha equal to 90 degrees. We had seen that on the last turn that as the load is decreased, current decreases, and there is chances that the current will fall to 0 before the beginning of next cycle. So that leads to discontinuous conduction. So for lower loads, conduction will not remain continuous and the characteristic will also change. So this shows the boundary between continuous and discontinuous conduction. So it's the boundary of continuous and discontinuous conduction. So this is the boundary. So after that boundary, after the particular that load torque that we call critical torque, the conduction becomes continuous, and thereafter the relationship is linear and the speed drops linearly depending on the value of Ra and K square. So this is the characteristic for continuous conduction. But when the conduction is discontinuous, the average value of output voltage that we derived in the last turn, it was Vm cos alpha minus cos beta plus pi plus alpha minus beta into E upon pi. Here you remember that beta is the extinction angle, that is the instant at which the current falls to 0. So this is the average value of voltage. You can put this value of V in this equation and you will get this equation. And then you can see that here there is a term E. So in place of E, I have written here K omega m. It depends on speed of the motor. So that I have divided like this: Vm cos alpha minus cos beta upon pi k, the first term, plus second term pi plus alpha minus beta into K omega m. In place of E, I have written K omega m upon pi k minus Ra upon k square into torque. Now you can see that here speed comes from right hand side also, speed term. So you have to, if you want to find the speed versus torque relationship, you have to take this term on the left hand side. So you take this term on the left hand side and take omega m common and then solve it, and you will get finally this equation, that is Vm cos alpha minus cos beta upon k beta minus alpha minus pi Ra upon k square beta minus alpha. Of course, it is the torque term is missing here, into torque T. So this is the relationship between speed and torque for discontinuous conduction. Now you can see here the slope as well as the no load speed, the first component, both depend on beta. Both depend on beta, and beta depends on the load on the motor. Higher the load, more is the current, and more will be beta. More will be extinction angle. So this depends on load. So this means that as the torque varies, both slope and this component will also change. So you can say that the characteristic becomes non-linear. So after the conduction becomes discontinuous, characteristics becomes non-linear. So let us see what will be the y-intercept. That is, what is the no load speed of the motor. So this is the no load speed. So what is the no load speed of the motor, that we have to think, so that we can complete these characteristics. So at no load, that is the torque is 0. This means that the average value of current Ia is also 0. Ia depends on torque. So Ia is 0. This means that Ia should not flow even for a short interval of time. So for all instants, the instantaneous current will also be equal to 0. So Ia will be 0 throughout. And if you recall those equations and circuit diagrams, you can see that for Ia to be 0, the value of E should always be greater than or equal to the value of back EMF, value of the armature voltage, because current that flows here, that depends on VA minus E. So even if for short interval of time, if VA becomes more than E, current will flow. So this means that VA should be equal to E, or you can say that the peak value of the voltage, armature voltage, should be equal to the back EMF E, so that current never flows. So this means that for this condition, E naught should be equal to the peak value of armature voltage. Then only current will be 0 for all instants, and then you will get Ia equal to 0, average current will be equal to 0, and the torque will be equal to 0. So this means that for no load condition, the back EMF E naught will be equal to the peak value of armature voltage in the whole cycle. So E naught is equal to VA peak. Now here I have shown two cases, one for alpha less than 90 degrees and other for alpha greater than 90 degrees. For alpha less than 90 degrees, you recall the equation, the waveform of armature voltage. It becomes like this, and you can see that in this case the peak value of VA, whether alpha is 90 degree, alpha is 60 degree or 30 degree or 0 degree, the peak value always remains equal to Vm. So for alpha less than 90 degrees, the peak value of armature voltage is equal to the peak value of the source voltage, that is Vm. So for alpha less than 90 degrees, VA peak equal to Vm. So E naught, that is equal to K omega m naught. Omega m naught is the no load speed, will be equal to Vm, and omega m naught you can write as Vm upon K. So no load speed will be Vm, which is a constant, upon K, which is a constant. So it is constant irrespective of value of alpha, whether the firing angle is 60 degrees or 30 degrees or 20 degrees or 0 degrees, the no load speed will remain Vm upon K. So you can see that this is the value of the characteristic for linear for the continuous conduction, and after that the no load speed will remain same So it is equal to like this. After that, characteristic becomes non-linear and the speed will be like this. And you can say that this is the, if, for example, if the conduction was not discontinuous, in that case this would have been the no load speed. But because of discontinuous conduction, characteristic becomes non-linear, slope changes, and the no load speed in that case will be more than the no load speed in the continuous conduction. That is when we give the motor the normal supply, DC supply. In that case, for this average voltage, this would have been the no load speed. But because of discontinuous conduction, the characteristic becomes non-linear and the no load speed will be higher than the normal no load speed. So this is the case. For alpha 60 degrees, if this were a continuous conduction, you would have got this no load speed, but the no load speed has to remain same as it was for alpha equal to 0. So it will be more non-linear and no load speed will be same as before. Similarly for alpha 90 degrees, if alpha is 90 degrees, the no load speed in the case of continuous conduction would have been 0, but because of discontinuity here, the current, the speed will change more rapidly and become equal to 0 for 0 torque. So it will be equal to this no load speed for 0 torque. So this is the characteristics for non-linear. And before, after that, alpha 90 degrees, you can see that the no load speed is now for alpha 90 greater than 90 degrees. You can see that this is a waveform here of armature voltage. The peak value of armature voltage is now equal to Vm sin alpha. It is not equal to Vm, it is less than Vm, it is Vm sin alpha. So peak value of the voltage is now less than what it was for alpha less than 90 degrees. So you can say that for alpha greater than 90 degrees, the peak value of armature voltage will be Vm sin alpha, and as the back EMF at no load will be same as peak value of armature voltage, then omega m naught will be equal to Vm upon K sin alpha. This means that beyond 90 degrees, the no load speed will also decrease. So you can say that for 120 degrees, this is the characteristics, and the no load speed is say Vm by K sin alpha. So if alpha is 120 degrees, so it will be root 3 by 2 or probably. So it will be that much less than the no load speed for alpha less than 90 degrees. Similarly for 160 degrees, this may be the characteristics. So this is the characteristic of rectifier controlled DC motor drive. Now here you can see the drawback of discontinuous conduction, that the characteristics becomes non-linear. The DC motor that we are using, and you hope that the characteristic will be linear, the speed distribution will be good, but because of discontinuous conduction, the characteristic becomes non-linear and it will be highly drooping. That is not expected from a separately excited DC motor. So this is a drawback of discontinuous conduction. So effort is made to limit this range as low as possible, and that can be done by increasing the inductance in the armature circuit. If you increase the armature circuit inductance, the range of discontinuous conduction may be further reduced like this, and in this region characteristic may become linear. So if inductance is high, then the range of torque for which the characteristic is discontinuous may be very limited, and most of the cases the characteristic will be linear. So this is avoided because of this type of non-linear characteristics. So this is all about today's lecture. So I have almost finished this unit. One more thing I will discuss in the coming lecture, and then this rectifier controlled DC drive will be over. So that is all for today. Thank you.